recording now. Yeah. So as of now, I was updated about this particular time because I think you had some clashes on Saturdays, right? So I'll be following that. In terms of syllabus, you will be covering representation learning and generative models as part of Factor 2 and Factor 3. This is the official syllabus and the official textbook. So if we get time in between, I might replace some of the contents with more modern topics. Like, say, I would like to cover maybe a bit of more advanced generative models. But if we get the enough time for that, we'll do that. The evaluation components, I think it was already announced by Professor Vignesh earlier. I think one of your quizzes is already done. You'll have another quiz later on. One assignment is, I think, going on for you, and you will get another assignment. The minor is upcoming, that has 30% weightage, and you have the major that has 40% weightage. Overall, you have the 100% of evaluation components. Some change regarding the lectures. For announcement and assignment submission, we'll still be using the Google Classroom, but for lecture PDFs and videos, we'll be using this particular website. So you can note this down. You can basically open this website and directly view both the lecture as well as the videos together. And I'll also provide a link to the previous set of, I think, the videos that I think Professor Vignesh had shared. We'll have a link to that as well. So that should not be a problem. Right. So we'll start with representation learning in this particular class. As the name suggests, we are trying to learn some useful features or useful representation of the input data. So given any, say, sort of task that you want to apply, either say machine learning or even deep learning, what you want to do is you want to pass that particular data through some ML model or deep learning model, through some network. So in any case, if I give you a set of text to deal with, you cannot directly feed that text into a network. You require some sort of numerical form so that you can then train or say pass it through some model. Because whether it's ML or whether it's DL, you are at the end of the day learning a mathematical function that maps that input to the required output. Say for classification, you're mapping an image to the corresponding class. So for that, we need at least a numerical format of the data. But if you simply provide numerical data, for example, of an image, for an image, you have the pixel information, pixel intensity information, the RGB values with you. And if you provide these directly to some model, these values individually does not have any meaning to them as much as, as to us as a human being, we look at images. It will not have a similar, the network will not have a similar view of these numbers. For them, these are just numbers to which to translate or map to the given, say, classes or something else. So it's always better, to learn some sort of representation or some sort of features from this initial set of numerical representation that you have of the data. Okay. And in fact, when you look at, say, traditional ML algorithms, they generally are provided with some representation of the data. And their task is to then identify some useful patterns in that data based on whatever task that you want to perform, with this classification, regression, whatever. Which becomes a bit of a tricky thing because ideally you want the representation of the data to be so good that you should be able to quickly identify the required patterns. And as a result, you will be tempted to use a human to identify the good, the good features of that given data. Which again is a tricky thing because as the data grows, involving a human in the loop becomes time consuming as well as a costly process. So if you are still trying to grasp the understanding of what a representation is, just think of a particular machine learning model that is used to recommend whether a patient has a particular disease or not. And obviously your AI model, at least till now, will not directly examine the patient. Instead, you will have a doctor which provides the model with some pieces of relevant information, like, say, whether the patient has some symptoms or not, whether the patient is already taking some medicines or not, and say the model maybe already knows a set of known side effects of current medicines and known uses of some medicines. Now, these pieces of relevant information that the doctor is feeding the model can be considered as each of these information can be considered as an important feature for this particular task. Remember, so given the task, the feature that is important for that task will also differ, right? I mean, it doesn't matter that a particular feature is that is good for diagnosing whether a person has a particular disease or not will be same as a feature that will be for based on which you'll decide whether an overdose of a given medicine has been given or not, or maybe the patient is not able to adjust to the given medicine or the power of the given medicine. So, depending on the task, the feature that is important may also differ. So that's where involving a human becomes a tempting thing to do, because a human can quickly understand, okay, for this particular task, I need this particular feature. For a different task, I need a different feature. But then that is not the ideal thing to do for a model, because you want to automate the entire thing. And which is what will end up happening. I mean, which ends up happening, say, in the deep learning models as compared to machine learning models, where you learn the representations as well as learn the process of extracting the required patterns in order to maybe classify or regress on the given model or given image or given data. Right. Now, the choice of representation, obviously, because if you're not choosing a good representation for your given task, your performance will not be that good. Therefore, the choice of representation becomes a very vital factor on the performance of your ML algorithms. No matter how good your ML algorithm is, if your representation itself does not cover all aspects of the given task, your machine learning model or deep learning model will not be able to understand or find out the correct classes for those things. Now, it will obviously, as I said, suggested that if you want to involve a human, that's fine. But if you're not doing that, or even for a or lay human being who is not an expert in a particular field, it will be very difficult to know which of the features you should pick up. Okay, specifically, if you're trying to do it through some human beings rather than trying to learn it. So suppose in a way that as we'll move back to the concept of an image, because that is what is easier for us as humans to understand, but harder for, say, your computers or models to understand. So if you want to write a program that is able to detect or maybe find out in which region of the photograph there is a car, or maybe you want to identify where is the wheel of the car and whether is the other parts of the car automatically from a particular photograph. So one possible feature of detecting a car may be that if I see a wheel somewhere, I can say that, okay, there's a wheel, then there must be a car linked with that particular wheel. Ideally, I mean, obviously there are situations where you might have uh, spare wheel lying in the road somewhere, and that is obviously not a good feature. But then you don't look at a single feature generally, you look at multiple features. You look at the wheels. So you'll generally not see a single wheel, you'll see multiple wheels attached to a single structure, and then you will have some windows, some doors involved in it. And then you can basically guess, oh, then this must be a car. Okay. But even with such level of, say, detailed understanding of what a car looks like, it will be very difficult for us to describe to a model or to a computer what a wheel might look like in just using, say, pixel values, because pixel values is what you will finally end up feeding the ML model or deep learning model. Okay. Because you're in terms of pixel values, where you're just simply looking at colors. A color of a wheel, first of all, might be different from different cars. Some may have a total black alloy wheels, and some may not have not have such wheels. Others, I mean, in different lighting conditions where you are looking at, say, night or day, or rain or in a storm, the same color of wheel might appear a bit different. Some of the wheels may not be perfect. Maybe that wheel has been in some accident, or may have been repaired in some way. And all of these factors will then make it extremely difficult for you to come up with one foolproof rule of identifying all the wheels in a given image. So the next best option that we have is to allow the model itself to learn what a wheel looks like. Or rather, just not looking at a wheel, we want to extract whether this particular image contains a car or not. So let's let's allow the model itself to learn what are the important features in a image that can possibly point towards that a car is present in a particular image. And this process of learning the representations or learning the important features of the given input is known as representation learning, which we'll see at least a few techniques for that. Okay. And you will be doing representation learning a lot, I mean, for different sort of tasks. And even though the name might change, but at the end of the day, the core concept is still representation learning, okay, which is identifying or learning the good features in the given input without having to explicitly handcraft features for a given image. Right. So as I was mentioning, handcrafting features initially, I mean, at least for the initial ML models, we used to actually have handcrafted uh, human design features of, say, different, say, in case of images, you had different types of filters that we designed, and then based on the output of these filters, we could then decide whether there is an edge or not, and that would combine such things and then come up with more complex parts of a given object in a given image. And this is obviously, as you can see, I mean, exactly defining features that can be useful for a given task is tricky in itself. And now, if I want to expand that particular model and perform another task, I'll have to again redesign all the features. Okay. Maybe for the different task, the required set of features may be different. And as a result, obviously, you don't want us as humans to encode all possible types of features. Rather, the model should be able to find out what representation is best working for it given a particular task. Okay. And that will be faster, and also that will be much more efficient if you can do it on your own. However, this will introduce a problem in deep learning that we'll look at later on, and we'll also see how that problem gets resolved. Okay. Right. So such kind of land representation will also will obviously, if I give you a new task, then based on the task, then the AI model can quickly adapt itself to new tasks and learn maybe new representations that are more relevant to the new task. And that is what happens in CME deep learning model. It will combine the feature extraction phase along with the ML learning phase, or the learning phase of the, I mean, of the given task. So say, for example, in simple, say, a traditional machine learning workflow, you will have something as a stage known as the feature extraction phase, or generally, if even it's not mentioned, you will see that some or the other, the input data itself has been extracted from somewhere else and only provided a, say, sample representation that has the important features. Or if not, that's not the case, we'll have a feature extraction phase. You might also have feature selection phase, where you, if you get a lot of features, but you identify which other features are important, and then you pass it on to an ML algorithm, which then comes up with the given output and tries to train based on this. So this part will generally not be learnable in a traditional machine learning workflow. Whereas what does deep learning do? Deep learning basically combines this entire phase. That is, you learn to solve a task, but you'll also learn to extract good features from the input. So you're involving the representation learning within deep learning itself, which in a way will reduce your load a lot, and also it will be able to quickly adapt to any given task without having to involve a human to identify some good features for that given task. Okay. Right. So the next important concept in representation learning are factors. Okay. When I say factors, just look at this particular image that I've shown over here. You have two sets of images, and suppose I know I have a black box model that knows how to create any given image. I mean, nowadays you have anyways deep learning models that can generative models that can generate an image based on your requirement. But this is the concept behind this thing. Suppose I have a black box model and I have a set of features or factors of variation of your image. Maybe in your set of images that you want to generate, the only thing that I can change are whether the person involved is a male or a female, whether the person is sad or is smiling, or whether the person is maybe is bald or is not bald. Okay. And based on this, I'll simply flip some of the switches and come up with the corresponding, say, image of a man who's a male, who's smiling and who's bald. Or maybe I'll come up with another version which is a female who's maybe smiling and has hair on her head, and corresponding can come up with this. So you can basically call these set of, say, features are as some factors of variation that explain actually the data that you have. Okay, because if I can know, ideally in an ideal world, if I can know all such factors of variation, I can then generate any given, say, image with any possible variation, given just a simple explanation or description of the given image, which is something we have been doing from now. I mean, from at least from the past 2 years with a lot of visual or uh, language and vision models, and that is where you provide, say, an input in terms of uh, so description of a given scenery and the image, and the model is able to generate an image that is able to exactly match the description. Maybe there will be some variations still because it's not possible to cover all factors of variation, but that's a general idea. I want to identify some factors of variation, and then that will explain the model the best, and we can then utilize them according to our need. So factors can also be considered as separate sources of influence. Generally, we tend to identify disentangled factors, factors which are independent of each other, because that's the best case scenario where you will be able to independently manipulate each of the factors without affecting the others. So these kind of factors are generally abstract concepts. You'll not have, in case of at least smiling and other things, you can at least, as a human being, you can identify these factors in a given image. But for, say, a computer, it's not always easy to understand what is happening in an image directly. So say smiling is maybe easier to identify. But when I say that, okay, this person is maybe sitting on a bench in a beach. So if I don't see, if the computer does not see a sea or a beach side sand, it's very difficult for the computer to know whether that person is actually sitting on a beach or some. So there are some concepts which are much more abstract and cannot be directly maybe abstracted from just by looking at an image. So these abstract concepts are factors of variations which we ideally want to learn. So if you can learn the factors of variation, then you can generate any set of images that you want. And that is, again, since we are going towards representation learning, ideally we would like to learn all such factors that can affect the given output or the given image. And if I exactly know all these factors, okay, the ideal case of representation learning will be that I have all the factors in my representation. Now, depending on the task, I can basically use a set of factors that directly affects maybe task one, may not affect task two, and say, but I'll be able to identify all these factors and correspondingly segregate only the factors that I need from for that given task. Right. So in general, these sort of factors are not very straightforward to identify directly. Maybe. I mean, just by looking at it as a computer, even as a human being, it might be a difficult thing. So, but ideally, we want to learn such factors. And as I mentioned, that most applications will want that in an ideal situation, we are having disentangled factors of variations. And obviously, for tasks which don't require that particular factor, we'll try to discard those factors. And in terms of disentangling, you basically mean that you get independent factors of variation, so that if you modify one of them, the others are not getting affected. So that's the ideal scenario that you want to achieve. And ideally, this obviously is a very difficult task because not all of these factors will be directly evident from a given input, say even say a voice or say image. And you will always require maybe some sort of a human level understanding of the data, which in itself is very tricky. Right. So, how does deep learning solve this problem? Deep learning does a hierarchical approach of identifying factors of variation or representation. So, what it does generally is, what we'll also describe in the next set of slides, is that initially, so deep learning models generally have a lot of layers. So, what it will try to do is, for the initial layer, it will try to identify very simple features, like say if there is an edge at a particular point or not, a vertical edge, or say a horizontal edge somewhere or not. At the next level, what it does, it combines such features and maybe tries to identify corners of, say, a particular image. Right? And as you move upward, you will see that the features that you learn are much more complex. So maybe if you're identifying faces towards the end of the network, you will actually see the networks are actually learning to identify some average faces. And these average faces and then can be combined to perform, say, some sort of a classification or whatever task that you're trying to perform. So we'll discuss this in the following slides. Okay. And the entire idea is that you learn simple concepts first and then build on the simpler concepts as an input and learn a representation on top of these simpler concepts. Okay. And you do it multiple times. So by the time you have reached a few layers, you're a few layers deep inside the network, you have already learned a very complex representation of the entire say image, which also is aligned towards how the task also wants the data to be or the representation to be. So in deep learning, because you're directly training the representation learning along with the training the model of to solve a given task, the task has a direct hand in picking the good representations or picking the required factors from the given image as well. So that's how, since you have brought the task into the picture, the task will now also have this particular influence on the representation learning as well. Okay. Right. So we'll just simply look at the concept of combining factors. As I mentioned, you are a deep learning model will generally try to learn very simple concepts initially, and then at the initial layers, and then try to maybe combine them, come up with much more complicated structures within the object, to identify the object. Okay. And specifically, if you have looked at, I think if you have done the ML course, you may have already seen this particular diagram, which is of a multi-layer perceptron, which is a very basic, say, a shallow network for your deep learning operations or say machine learning operations in general. And what you will see is that with if you approach this problem again with the same concept of combining simple models into a more complicated model, you can actually consider every perceptron as a simple model. So this may be one simple model, and this can be another simple model. And what you do is that after every stage, you get to combine these models. And once you combine these models, so what you're doing is that you're learning, say, separate factors of variation of a given input, and then you're combining these factors or maybe getting to choose the best factor because you have activation functions over here. So you are getting to choose the best factors that might affect the label of this particular task. So for example, if I'm looking at classification, some of the factors which do not affect the classification of that particular image will obviously get ignored in that case. Okay. Right. So that's the general idea. And if you look at this image, which is exactly what I was describing, initial layers will have very low level features like say edges and all. And as you move upwards, we'll see much more complicated features. You'll see say parts of your face may not be immediately evident in the second layer, but at least higher up the hierarchy, you will see that much more complicated features like say faces. Portions of your faces will come in. And towards the end of this thing, you will see actually the entire face getting extracted at some level, and the features or representation that you see are much more complicated. That's the general idea behind how your deep learning models tries to approach this problem. Obviously, one factor that we are not considering at this particular stage is how to disentangle these factors. So there is no guarantee that this particular factor that you identify over here is totally independent of here, this factor. So a minor change to this factor might also end up at the end affecting these factor as well. So we are not doing any sort of disentangling at this point, though there are specific approaches to performing disentangling. So we'll maybe briefly look at that as well. Okay. Right. And in all of these cases, as you look at the type of features that these particular intermediate weights are trying to identify, these weights then therefore act as sort of like a filter or a pattern detector at each of these levels. So if one of the pattern matches with this corresponding eye, that particular output, when you look at the output of this given layer, that particular output will become very high as compared to the other outputs. So in a way, at every stage, you're identifying the relevant information present in, say, your image, and those outputs will be higher because in all of these cases, you're simply performing multiplication, right? You have WX plus B happening at every stage. Okay. So whatever is happening, you're always, whenever these two are aligned. So suppose if you have a particular eye that matches with an eye of a given image, this particular value will be very high. Okay. And comparatively, if there will be other factors as well, which do not match with this given weight, those values will be low. So in a way, what you're doing for any given image, you're propagating the matching patterns with a higher weight to the next set of layers. So by the time you end up maybe at this particular position, you already have a very small set of relevant features. Okay. Other features are also present, but their values will be lower. So when you come up with the final contribution towards each of the classes, these features which have been identified in the given image will have a higher contribution towards the predicted class. Okay. And that's the general idea when you look at any sort of thing. And another thing that another level of understanding you can come up with the concept of MLP is that you can consider each of the MLPs that you have. So you have this MLP over here as a simple classifier in itself, which learns maybe an average representation, or you learn a very simple representation of a given image. Suppose you're running it on an MNIST data set where you have images of numbers from 0 to 9, and each of the perceptron runs a different types of image. Okay. So if the given image matches any one of these patterns, that perceptron will have a very high output compared to the other perceptron, and finally you get to predict the class of that particular image based on the identified features. Okay. And as a result, because you're learning different types of versions of the same number at different perceptrons, you can capture the subtle variations in the data itself as compared to if you're only using a single, say, perceptron. Okay, that's the power of compounding, sort of. So you are identifying simple features first, you are then combining them to come up with much more complicated features, and those complicated features also gets combined further. And in a way, you're identifying more and more complex uh, versions or complex objects in the given data, and also different versions of that same object. And this is general idea. So in the first layer, you will generally identify, say, the edges on some other types of filters. Okay. And initially, say you'll have a set of pixels, which are the input, and then you start identifying edges. And from edges, you can move on to, say, corners. And then once you move further up, you will see more and more complex pixels. Okay. We'll move on to the representation learning part, but before that, we'll see what a good representation should have. So a good representation obviously will be task specific. We don't go to generic representations that are good, because even though, say, your representation might contain a lot of factors of variation, not all of them might be useful for a given task. So if you also incorporated such factors which may not be useful for a given task, you'll end up losing a lot of computational power in identifying some bad features as well. I mean, these necessarily may not be bad features, but may not be relevant for your given task. So ideally, if I only want these three factors, my best representation will be such that I have a dimension of 3, and each of these dimension only contributes to whether the gender, whether the person is smiling or sad, or whether the person is bald or has hair on. Okay. So when you think of, say, a good representation, ideally what you want to do is that we'll come to the unsupervised setting later on. I'll explain this further later on. But for now, when you think of a good representation, you would ideally want that if you had, say, an initial image of, say, 32 cross 32, and obviously that comes out to be 1024 pixels, I ideally want to have, if I know that there are, say, maybe 20 factors of variation, I ideally want to reduce this entire set of input into a vector of, say, size 20. And each of these 20 factors of variations will be independent of each other, so that I can simply flip a switch on one of these factors and correspondingly modify the image that I have in here. And that is something that I'll consider as a good representation for my given set. Okay. Right. Okay. And also, I mean, in the process, we should, we want to do this reduction so that our basically problem becomes very easy to model, because learning a model on 1024 input and learning a model on 20 input is comparatively, this will be easier than this particular set. So ideally, we want to reduce this representation to only the required set of factors of variation, or required set of features. And for this simplicity, however, we should not throw out useful information, because if you do so, then there's no point in performing the next step of basically classifying the image, because we'll have lost some good features in, while trying to make the model too simple. Okay. So we need both. We need a good representation that has only the relevant information present in the representation, and we also want it to be we want the task that follows up on this particular representation to be easy to learn from this particular setup. Okay. So now we'll come to,
Sir,
idea of how.
take a quick question here.
Yes, yes,
Yeah, sure. So we have seen this kind of concept in CNN as well. Like we apply a kernel, we apply a filter to extract
yes, yes.
different
Mhm.
low-level features, and then you combine in a FC, fully connected
Yeah, yeah,
network. How
yeah.
that is different from this one? We're still trying to make sense, like what's happening here.
It is not different. I am simply explaining the concepts of deep learning that will come in handy in the following slides. It's the same thing. I am simply
Mhm.
describing deep learning for you. Okay, in terms of difference, if you say that when you're doing it in CNNs, you had convolution operations going on over there, and over
Yep.
here I'm simply considering a simple, say, fully connected network. But the idea is the same. It's the same. Okay.
So it's kind of concept, separate perspective. You are trying to make some
Yes, 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 yes,
background
yes,
for
yes.
that. Okay, okay,
Yeah,
fine.
I'm
Got it.
laying a background, and now I'll start on with the
Yep, yep.
representation.
Okay. Thank you, sir.
Okay. So, one problem that see till now we have been seeing that representation learning is obviously a good approach as compared to maybe learning, maybe making handcrafted features. And one approach of representation learning was to simply train your given data on directly on a deep learning. I mean, using deep learning to directly train a model on your given input. And in the process, deep learning would learn a good representation for a given task as well as solve that given task. So you would have combined both of these things. But it generally was found that when you're trying to train a deep network, especially in this era of say 2006 and earlier, people were finding it very difficult to converge, and a lot of factors were contributing to this. The data also was not enough. I mean, when you want to train a deep learning model, you did not have maybe enough labeled data, and also you had say maybe limited computing power and also other factors that came into play. High speed computing was also maybe extremely costly and beyond the maybe the reach of say some I mean ordinary researchers. But then something happened in 2006, which actually brought back interest into deep learning, and that is what we'll look at. And that concept was the concept of greedy layer-wise unsupervised pre-training. Okay. And it was able to utilize this concept that learning a shallow network is easy. I mean, if you simply learn one simple multi-layer perceptron on given data, at least it will not be as good as maybe a very deep network, but at least convert the model will at least converge to a particular lower loss, and you can then maybe stop and say, okay, this particular single layer model can only achieve this much accuracy, but that was achieved comparatively easier. But it turned out that if you used a much deeper model, the either data availability was not much, so you're actually maybe you're overfitting your model to the less data, or maybe the computing power was not that much. So all of these factors had contributed a lot to reduce interest towards deep learning, and that is where your greedy layer-wise unsupervised pre-training comes into the picture, and this provided a way to improve the performance of your deep learning model, and by performing a very unique way of representation learning. Uh, so before starting this, I'll again remind you that initially ML models had a separate feature extraction phase, and then you had the ML model, and what deep learning is was combining this entire thing. Okay. But what deep learning was doing was that you had your entire network, deep network, and given your input image, it was training the entire uh, all of these layers together to identify the correct class given the given input. Okay, and optimizing all of these networks, all of these layers together was turning out to be very difficult. Whereas maybe optimizing a single layer or a very shallow network was comparatively easy, and that is what this particular method tried to play upon. It tried to take a greedy approach, and greedy approach generally involves dividing a very hard problem into say smaller problems and then solving it, and that is what comes into the picture. And also the unsupervised nature of this pre-training ensured that you do not need too much of label data for at least the pre-training phase, which is again one thing that was going in support of this particular setup. Okay. Right. Now, greedy layers and supervised training was proposed as a way to initialize the parameters of a deep neural network. Okay, and it was done in a layer by layer manner. Okay. So the approach was that you will first basically identify the best parameter for or best initialization for the first layer, and then you freeze it and you move to the next layer and then you freeze it. Okay, How you do that, we'll say that the process for that, how you basically end up learning the layer, because you will not be using any labeled data for this particular task. Okay. And this particular setup relies on single layer representation learning. Okay. And each of these layers will get trained as a standalone model, okay, at each step. And what happens at the end is, because you have a set of layers that you're training, and obviously you have your input, what you will end up doing is that you will separate out this particular layer, maybe the first layer, and only provide this particular input and train only this particular layer. Once this layer is trained, you will freeze this layer and open up this network, this next layer as for training. So this entire thing provides an input to this given layer, and you only train a particular layer. Okay, we'll see the details of it in much more detail, and so on and so forth. You keep on doing this till you have finished all the layers, and you're only left with the classification layer. Okay, and then you go back and fine tune the entire model on the initial on the original task that you're supposed to work on. And that's the general idea behind your greedy layer based unsupervised. And we will be explaining this process in terms of an autoencoder. Okay, so I'll briefly discuss some of the terms involved also in this particular setup. Okay, most importantly, you have the autoencoder, which, as the name suggests, it's performing some sort of an encoding operation. But in terms of architecture, it has an encoder as well as a decoder. So encoder will reduce the dimensionality of your given input, and again it will try to reconstruct the input at the output layer. Okay. So ideally, what is going to happen if I in a way, I'm compressing the information and I am again reproducing or reconstructing the initial representation. What I'll end up happening is that I will learn such a set of representation that holds all the information of X and discards the additional information of X, so that I'm able to reconstruct X back. Okay. So in a way, you're learning the structure of X, the core concepts or the factors of variation of X, and based on that, you can now move ahead, and that is a good representation for X itself. So autoencode is also a very good way of performing dimensionality reduction. Right. So the encoder function converts the input data into a different representation, and the decoder then subnetwork then converts the new representation back to the original data. Okay, and that's the laws that will also apply. Yes.
So this encoder's inside mechanism is actually the same as that greedy layer thing that you.
No, we'll be using this encoder concept into the greedy layer thing, greedy layer pre-train. So just describing an autoencoder before that. So obviously the idea is that it has to preserve as much as information as possible while performing this autoencoding operation, because if it's not able to preserve information about X, it will not be able to reconstruct X back. Okay. And that's where we'll be utilizing this particular concept while training the layers as well. Okay. And you have different types of autoencoders. Specifically, we'll look at maybe one additional types of autoencoder today itself. Maybe the next class, to understand how this is working. Okay. So if just for a second, I'm changing your problem setting, and I'm only asking you to learn dimensional reduction for a given, say, set of inputs. So if you have an input, say X, and this is the input, and what I want to do is basically learn a compressed representation Z, okay, which retains all the information of X, and therefore I can use this as my new input. Okay. If that's the idea, autoencoder will fit right into this particular setup, and all you have to do is you have to learn, basically, you have to set up this particular model in this way. You have an encoder layer with a particular weight, you have a decoder layer with a particular weight, and the loss function that you'll end up using is basically the difference between the reconstructed X and the original X. Okay. And once you train this thing and you try to optimize this particular loss, the difference between X and X bar will go on decreasing to a point. Maybe you have a very low loss. That means you have very low loss of information, which ensures that now what you have done is you have learned a compressed representation that maybe preserves most of the information that was present in X, and you can now maybe discard the larger representation and only use this particular setup. And also, since you have already trained this particular encoder model, you can simply use the encoder model and convert all your input data to a lower dimension space. Okay, that way you save a lot of computing power. Maybe for the following tasks and all, you can simply use the lower representations, lower size representation. That's a very general use of, say, autoencoder, the concept of autoencoders as a dimension reduction tool. And the good thing about this is that does not require any sort of labels. Okay? You don't need a class
So,
label or any labels.
one doubt,
Yeah.
one general question, like why it is
Yes. Yes.
auto?
Why is auto?
Yeah.
Autoencoder, why will you call it autoencoder? Right, I mean, because in a way what you're doing is that you are you're performing automatically dimension reduction. That's one of the reason. I don't remember the exact reason why it's called autoencoder, but you are performing without looking at any specific, say, PC or other algorithms. You're performing automatic dimension reduction in this case. Okay. Maybe that's one
So
of the reasons.
number
Other
of
reasons might also.
layer will be like decided automatically, or how it is?
No, no, no. That automatic decision that comes into play in neural architecture search, that's a different concept altogether.
Okay.
So I think
This
this is
you
unsupervised reduction. That's the reason it's calling autoencoder. You need not to label this to
there's no label
identify
required.
the
Yeah, that can be
yes,
another
yes.
factor also. Okay. So that's the general concept of an autoencoder, which we'll use for our greedy layer-wise representation learning. And obviously, if you consider this, will you consider this as supervised, this particular setup?
No.
This will not be supervised, right? I mean, you don't have any label associated with it. Some may call it self-supervised because you are using the X itself as a supervision, the input itself as a supervision. But generally, you will not call it a fully supervised setup. It's an unsupervised or a self-supervised setup. Right? And for that, we'll briefly touch on unsupervised learning. We'll come to it much later on while discussing other topics. But the general idea is that in any given setting, whether it was in 2006 or even now, there will be some areas where it will be very tricky or difficult to obtain labeled data. Specifically, maybe you look at fields even nowadays and say for medical images, it's very tricky to get anonymized data of patients if you want to train a model on those. Even though, I mean, there has been some headway into this thing, but there will always be cases where you don't have enough data. And if you have to perform some sort of a supervised training in order to train a classifier, maybe, or maybe some other task, if you have very few labeled samples, okay, if you have since your models that you generally end up using are large models, those can easily overfit on the limited data that you give. Obviously, you train on larger models so that you can get more better representation and better features and better accuracy or better performance. But if you don't have enough data, you don't have an option because your large model will overfit on your label samples. Okay. And comparatively, humans, on the other hand, can learn with extremely less amount of data. You look at one cat and then you're expert in, I think, most of the cats that you identify on the road. Okay. Even though their texture, the skin and the fur, everything is different, you'll still be able to do. So in a way, you may have transferred some existing knowledge into this particular task as well. So you may have acquired some previous knowledge either innately or through some other way, and you're utilizing some existing knowledge to also help a new task. I mean, you may have learned some other task, and you're learning and utilizing that particular knowledge to identify or perform a different task as well. And that's generally the concept of what you try to do with ML models or DL models as well, is using some sort of a non-supervised or unsupervised or a self-supervised model. And that is the idea. That is, you're learning to train a model or learning without access to labeled examples, okay? Or maybe with access to self-labeled examples. I mean, the more recent trends tends towards self-labeled examples, which may not be exactly the task that you want to solve. Okay. Okay. Let's now finally come into the greedy layer versus unsupervised training. Okay. We call this 3D layer-wise unsupervised training. Each of these terms are important in itself. You call it greedy because you only try to update one particular parameter at a time, okay, one particular layer at a time, and then you freeze that layer and train the other things. That's why you also have the layer-wise. And we call it greedy because you're not thinking about the final task of, say, classification. Rather, you're only thinking about identifying the good representation in each layer. This process itself will be unsupervised because you'll not be utilizing the labels that are provided for the images. Okay, and as a result, if you have access to a large amount of, say, unlabeled data, you can utilize that directly for this unsupervised pre-training phase at least. And maybe once you're done with the pre-training, you can fine-tune a model on the limited amount of, say, label data that you have. Okay, and it's a pre-training step because this will provide a good initialization for your given model, and which will go ahead and then train on the given task. Right. So I'll briefly come to the setup itself. Okay. This is the thing that we have already covered. It's called greedy because all the layers are not jointly trained. It's unsupervised, and you're doing it one layer at a time. Okay. And this thing should be noted that when you're training the upper layers, I mean, if you're moving from down to up, if you'll train the lower layers first, you'll freeze them, and you train the upper layers, but then you don't update the initial previous layers. Okay, so you always go forward. So if you have trained already a set of layers, you will not ideally go back and again update the initial layers. So we'll see that. I mean, the process itself. Okay. Okay. And there will be two main phases of this given setup. You'll have a pre-training phase and you'll have a fine-tuning phase. As the name suggests, pre-training phase will do this greedy and layer-wise unsupervised pre-training, and the fine-tuning phase will then unfreeze the entire network and maybe train for a few epochs on the target label. Train the entire network on the target. Okay. And there can be, I mean, recently you no longer maybe want to do exactly greedy layer-wise unsupervised learning now, but you apply some more recent unsupervised learning setups. But the general architecture of this problem is still the same. You pre-train your model. In fact, you can get some large language models also online, which are pre-trained on a given task, and you can then fine-tune them on your given task. So that's the general idea. And that was a new concept in those days, initial days, when they found out that actually pre-training the model would improve your performance. Get a very big boost to your performance. Okay. Right. Now, this is the general setup which we'll discuss now. That should clear out all the doubts. So suppose you have a given model, okay, that has an input X. Okay. You have an input X, and you have a model, just a second, which has a set of layers. So you have W1 for the layer 1, W2 for layer 2, you have W3 for layer 3, you have W4, which is basically the classification layer for layer 4. Okay, and you want to train this model for the classification task, but I want to perform pre-training greedy layers and supervised pre-training before I perform the classification task, so before I train for the classification task. So maybe initial model you're training on some set of images which are images of size, say, 32 cross 32. You have you flatten them and you have a 1024 size vector that represents the image. Your first layer, which has some set of weights W1, will reduce it to a vector of size 512, and then the next one reduces to 256, then the next one to 64, and finally the classification layer gives you an output of size 10, representing the 10 classes of, say, the MNIST data sets from 0 to 9. Okay, and now I have to perform unsupervised layer-wise pre-training. Okay, so the first thing that I do is that I'll only train W1. How do I do that? I'll bring back the concept of the autoencoder that we just discussed. What we were discussing was using an autoencoder to reconstruct the original input. That you can see is exactly what is happening over here. This is W1 that you want to train, or that you want to find the good initialization for. So what do? You take the output of W1 and pass it through another layer. Okay, that gives you back the 1024 sized input. Okay, and then you add a loss that reduces the distance between, say, X bar and X. Okay. And you do it, say, for a few epochs, and once the loss has converged, it is reduced a bit, you then will stop this particular training. You have learned basically the initial representation that's good for, say, W1, and you'll move on to the next layer. Now look what happens at the next layer. For the next layer, the input to the next layer is not 1024, but 512, right? So what you do is that you consider H1, which is the output of W1, as an input to H2. This part is already frozen. Okay. And once you provide H1 to W2, W2 will then convert it into a vector of size 256. And then you will try to reconstruct it back, the 502 size vector, that is H1 bar. Okay. And you want to train this particular layer by reducing the distance or reducing the difference between the original H1 and the reconstructed H1. That's the idea. So you do this for a set of epochs, and then when you find out that the loss has gone down a bit, and I mean loss has gone down, and the loss has basically converged, it's not reducing anymore. So then you can maybe assume that W2 is properly updated in terms of at least the unsupervised learning that we are trying to do. It has retained enough amount of information about H2 to be able about H1 to be able to reconstruct H1, and then we can then finally move on to the next layer. For the next layer, we can see that W1 and W2, both of them are frozen. So the output H2 becomes the input to W3, and that is what we try to reconstruct back. So we try to reconstruct back the H2, and once we do that, obviously initially the results will not be good. Initially your reconstructed H2 might be very different from H2, original H2. So you will perform this training using the loss of where you reduce the distance between, say, H2 bar and H2, and you do it for a few epochs. Still you're satisfied that okay, the loss has gone down. I am able to reconstruct H2 with good amount of uh, uh, knowledge being retained. So once that is done, you have trained all the intermediate layers. So you're now left with the classification layer. For the classification layer, we generally do not perform the pre-training. So what do? We have the initial weights or the weights that give good representations for W1, W2 as well as W3. We now open up the entire network. Okay, we open up the entire network, and remember, in all of these stages, if you look at it, we always discard this portion. Okay, you have an autoencoder, right? You have an encoder, you have a decoder. We always keep on discarding the decoder portion because that is not part of an original network. Okay. So in this case, you have discarded W1 bar, you have now discarded W2 bar, and you'll finally discard W3 bar. And this is now your final network, for which at least W1, W2, and W3 have been initialized to a good initialization parameter. And now what you do, you perform a training on the entire network on the given label data. Till now, you were utilizing any data that was available to you. Maybe if you did not have any other data, then you have basically the same set of data. But at least we are not utilizing the label of these data. And but now what you do is that you perform a fine tuning for a few steps or a few epochs on the entire network, and then you and turns out this simple process of pre-training before you train the network on the given classification task is able to boost the performance of your network significantly. Right? And this concept, as you can see, it's a very simple concept, and people at that time were looking a lot into this particular setup as to why this particular simple pre-training setup is working that well. Okay. And this was leading to substantial improvement, at least in the test error or the classification accuracies and all. So what researchers came up with was a set of ideas about why this particular setup was working. So the first idea was that since your unsupervised pre-training was providing initial values to the parameters before your fine-tuning step, this was having a very good regularization effect on your model. Remember, in any sort of regularization, we were trying to restrict your model parameters to maybe a good region of the feature space or a good region in the parameter space, so that you get your maybe you're trying to make the parameter weights much more sparse, or you're trying to impose some sort of a structure on the model so that it is not overfitting to your given data. So in a way, when you're choosing initial parameters for your deep learning network, researchers assume that maybe these initial set of parameters that you have found out was having a good regularization effect on your neural network, and that when they had also done some set of experiments and found that generally when you pre-train a network in this particular way, the next step of fine-tuning does not require to change these weights by a very large margin. Maybe so if you have a large space where your initial set of parameters may be lying, and initially if you start randomly training the network with random initialization, you may be shifting from one point to the other while trying to find the best parameters for a given task. But if you did pre-training, turned out that the set of parameter option, the space itself had shrunk. I mean, you were already placed in such a good place such that you did not have to move too much. So the parameter or the representation that was learned using the pre-training phase was actually able to move your entire model to a region where you did not require then too much of training to come up with a better performance. Okay, that's the general one of the assumptions that they were making, that maybe this is the case why this particular setup is working that well. Okay. Okay. And I think this actually also led to a lot of research then into, say, initialization parameters. The next idea was possible next idea why this thing is working is that because while training your network, you are actually forcing the network to learn about the structure of the data. Okay. Because what are you doing is that you're not caring about the classification or the other tasks, supervised tasks that is going on at the end. You're greedily only trying to learning the factors of variation at each level. So you're learning the factors of variation of the input data at the first layer, the factors of variation of the first hidden layer output, second hidden layer output, and so on and so forth. So whatever you're trying to do, you're always trying to extract good features in a hierarchical manner, okay, and without using any sort of supervision as such. So that was forcing the network to understand the core structure of the data itself. Okay. And maybe that is one of the reasons why once you move to a simple fine tuning, you already have parameters that are extracting good features. If you're already extracting good features, the overall error that you encounter with a fine tuning task might be comparatively lower, or maybe it even if it is slightly higher, it will take you much less amount of decent to basically move the parameters to the correct region, because you're already at a place where the parameters or the weights are able to identify good features within the data itself. And these kind of factors and features that you have identified through simple unsupervised training may help in, maybe useful for some of the supervised tasks also that you're doing. So for example, if your unsupervised learning setup has learned to identify the location of your object, okay, because you're trying to learn maybe those features in that is best able to reconstruct back the image. So your image contains some objects. So if my unsupervised training has learned to identify which of these set of pixels actually is an object and which is a background, in such a case, once you use this particular setup to fine tune, maybe for those tasks, it will become easy. Okay, I think some of you have classes from 12. We will continue this in the next class, that is tomorrow.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Yes.